Hi, my name is Giselle Alejandra and I'm going to present my final project for neural networks entitled Artificial Neural Network Based Assessment for IEEE 30 Bus Load Flow Solution. So for the content, I'm going to present the number one objective of the study, the motivation behind this study. Number two, where I get the data sets. Number three, the base model, how I um, identify the model or how I structure the model architecture. Number four, the performance metrics, what metrics I used in this study. Number five, the results. And number six, the conclusions. Load flow is one of the study being conducted in power system analysis. Since our power network continuously growing over time, computer simulation is beneficial. But software simulation tools are computationally expensive for large variety of networks, and utility model accuracy can be inadequate. That's why power industries adopting the use of artificial intelligence in power system study. Now, the goal of this paper is to create a deep learning framework for approximating power flow simulation results and evaluating performance for IEEE 30 bus test case and assess the capability of ANN in power system load flow solutions. So basically, this study is pure assessment, not to create a novel output. This suggested ANN-based load flow solution is anticipated to be faster than traditional numerical analysis load flow problem solvers. So the subsequent sections of this study will provide the proposed ANN architectures and the selected input or output variables used in the training and testing of the data. Now for the datasets, the proposed methodology was tested using IEEE 30 bus system. And this IEEE 30 bus system was the test case used by previous study by VL Paukar and MJ Ryder. Simulated a related study with 10 load situations, 6 of which were used for neural network training and 4 for testing. So this paper is designed to simulate 30 load situations, 24 of which will be used for training and 6 for testing. Now the data set was from the study created by Dr. Dan Wu and Dr. Bin Wang, entitled the Holomorphic Embedding Based Continuation Method. So it was simulated through MATLAB and created to have a benchmark dataset for finding many or all real-valued solutions to algebraic power flow problems. It includes a large database of real-valued power flow solutions for 5 common IEEE test cases: 14 bus, 30 bus, 39 bus, 57 bus, and 57 bus modified with a variety of loading conditions. So this paper is focused for IEEE 30 bus test case and will use 30 load scenarios with a total of 183,660 samples with training data of 110,196 and validation and test case of 36,732 samples. For the neural network architecture, Figure 2 shows the schematic diagram of the construction of the adopted neural network model used for the load flow problem. Since the diagram is layered feed-forward ANNs, the back propagation algorithm is used. This means that the artificial neurons are structured in layers and send signals ahead with errors propagated backward. Neurons in the input layer provide input to the network, and neurons in the output layer give the network's outputs. So there could be one or more hidden intermediate levels. The backpropagation approach employs supervised learning, which means with provided algorithm samples of the inputs and outputs, the network to compute desired, and then it calculates the error, the difference between actual and predicted outcomes. So the backpropagation algorithm aims to reduce this error until the ANN has learned all the training data. The training begins with random weights to fine-tune them to ensure that the error is as small as possible. There. So the input layer's dimension is the real and reactive power injections and the voltage magnitude times the 30 load scenarios. Now the output layer's dimensions are the voltage magnitudes times the 30 load scenarios. So to minimize the error between the expected output and the actual output when training a neural network to complete a task, changing the weights of each unit is a must. Therefore, it ought to figure out how the error varies as the weight increase or decreases slightly. Recent studies on using neural networks for power flow approximation have used multi-layer fully connected structures. As a result, this paper optimizes the number of layers. Type of activation will be used in this paper is TAN and ReLU, and a number of hidden units using a fully connected architecture as a baseline model. It is projected that neural networks will be able to understand the voltage patterns associated with training examples and gain the ability to generalize and solve new load flow problems. So during the training, the ANN must learn certain voltage patterns as will be demonstrated later. The suggested neural network was trained and Adam optimization was utilized for training the model using a mean square error loss. So to prevent overfitting, the model network features an early stopping function with patience of 10, and it also uses a model checkpointing method to make it easy to go back to the data if something goes wrong. So the training will have a 100 epoch and a batch size of 32. So according to the findings, the amount of training data necessary for fully connected models grows with the size of the power network. So with more than 1,000 data, the linear regression model's performance does not improve. So with the size of the power network, the advantage in implementing the fully connected network over the linear regression baseline diminishes. So for the multi-layer fully connected network, the mean squared error on the validation set as a function of the size of the training set. Each model received 100 epochs of training, which was more than enough to minimize the loss function fully. Increasing the number of layers in a fully linked network did not enhance performance much. So the fully connected network functions well when simulated in an IEEE 30 bus network. The power network and the amount of training data available determine the relative performance of the fully connected for TAN and ReLU activations. The TAN activation, on the other hand, produces accurate findings for a particular network and operating situation. The model's validation and training sets have identical errors, which is to be expected given that the validation and training sets are drawn from the same distribution, thus predicting the values from the actual. It has been proposed to employ neural networks to compute bus voltage magnitudes to solve the power flow problem. The backpropagation approach for feed-forward multi-layered networks was used to get small MSCs without sacrificing the ANN's generalization capabilities. To define the most appropriate multi-layered structures, it was necessary to pick input variables carefully. The suggested ANN-based load flow methodology was tested using the IEEE 30 test system. A total of 110,196 load flow generated cases were randomly selected for training and 36,732 for testing out of 183,660. The mean squared error of the tested power systems training and validation instances was 0.0363. This number shows that the simulation correctly anticipated the trained data, demonstrating the utility of simple multi-layered neural networks in systems applications. The model will be particularly beneficial for real-time applications to power system challenges, particularly those involving many load flows. So there, that ends my presentation.